So let's write some net ion equations for acid and bases. Many students have trouble writing acid-base net ion equations, really because they just don't know what chemicals completely dissociate, and those would be your strong acids and strong bases, and they don't know what chemicals can ionize water, which really means when they react with water or components of water, will they actually reform the acid and base? So really the easiest way to go about this, so that you know what chemicals will spectate and you can get rid of, is identifying who your strong acids and strong bases are. Strong bases, I think, are the easiest to know because they're nothing more than the group 1 ions, right? Lithium, sodium, potassium, rubidium, cesium, and those are the most common, of course. And these guys are always soluble, right? You should know your solubility rule. Group 1 ions are always soluble. So we talk about a strong base. We're talking about the ability of these salts to completely dissociate because they're very soluble. And if you have a mole of lithium hydroxide, you get a mole of hydroxide ions. So these liberate hydroxide ion, which of course is a very strong base in of itself. So we call strong bases, okay, those salts that can completely dissociate and liberate this hydroxide ion. Don't forget there's group 2 ions, and there's a select few that are +2, but big enough to not have strong Coulombic attractions. And of course, it's all about Coulomb's law, if you know me. These guys are +1. They're relatively large. They get smaller as they get become ions. These guys are +2, so they're smaller. So we should know that magnesium, beryllium, those being row 2 and row 3 elements, those guys are actually +2 and too small, which means their charge density is high enough for the hydroxide to stick to them, and they're going to have high Coulombic attractions and not be soluble. So you should know these, and these are your solubility rules for hydroxides in general. So if you know them, you know who your strong bases are. So any other base that's not one of these group 1 alkali metals, right, from alkalinity, and the alkaline earth metals, right, also alkalinity is a word for basicity, okay? If you're a metal with a hydroxide, you're a weak base, and there's some other weak bases like ammonia or nitrogen-based organic compounds. So knowing who your strong bases are tells you that these guys will dissociate. And now why do I mention this? Because what gets confusing is, well, what about these ions here that result? You know, the lithium, the sodium, my friends, these are all going to be spectators, right? For the most part, these guys will not make any or ionize water to any extent. So all of these will just float around. And so it's important to recognize that the cation from the strong base will be a spectator, and you can eliminate these from your net ion equations. Now your strong acids are something that you may have a tablature for if you have Kas. You'll notice the Kas listed are extremely large. Sometimes they give you the numbers that are, times 10 to the 9 or 11, or sometimes just say very large, because the Kas, which are really the concentrations of the products over the concentrations of the reactants, because these guys are essentially just like the strong bases, completion reactions, they go forward completely, meaning that there's almost very little reactants left and a lot of products that are made when they quote reach equilibrium. I say quote because they're really completion. And if there is an equilibrium position, it favors the products almost completely. So it makes numbers that are extremely large and almost become undefined if this becomes a 0. So in any case, all Kas that are smaller than 1 are weak acids. So know these if you have to, or have a tablature. These are the top 7 strong acids. Now, what do I mention them? Well, they or their conjugate bases, okay, and we call them conjugate bases because that's what's remaining after the acid dissociates a proton here, all right? And we call them conjugate bases by the definition of what's remaining after the acid dissociates, but really they're not bases. They have really no ability to ionize water. They're also going to spectate, okay? Why? Because, well, if iodine could ionize water and reform and go in the reverse, you couldn't have these strong acids. What makes them strong acids is they almost completely go forward. And it's a completion reaction, which means these conjugate bases really have no ability to go in the reverse, pull a proton from water and H3O plus to reform the acid. It's really important you get that. So guess what? they spectate. So if you're having trouble understanding who's going to spectate, well, it's the conjugate base of this strong acid. It has no ability to go in reverse, so it will not ionize water back into, okay, the acid, or an H3O plus, okay? And the ion of the strong base, because it doesn't reform the base, if you want to think that way, I like to think that, hey, these are always soluble ions because they're just too big of an ion to attract for the most part, any case, especially the group 1 ions. These are also your spectators, all right? So that's one way to think about what your spectators are. Another way, and I give this out to my students today after school, they maybe think about this another way. If you've got a strong acid, weak base scenario, the strong element, in this case the acid, will pull and make the other chemicals split up. Let's go get to it and get to some examples. All right, I start with this example here because this is the one people get wrong all the time. And the reasoning for this is they think that always the net ion reaction of this reaction here is going to be as follows. So in any case, let's go look at it. HBr is a strong acid listed above. So I like to tell my students to write that broken up, H plus and Br negative. It's not really together in solution. Okay, I know the H plus is probably held with water and H3O plus, but regardless, KOH is a strong base, so in solution it really is K plus and OH minus. These guys are not really together. We write them that way. So these are completely strong acid, strong base, so you can see what's going to happen here. We're going to make, hey, the H plus and the OH is going to very spontaneously make water, okay? And we should recognize the fact that bromide and K plus are spectators. Bromide is a spectator because it's a conjugate base that does nothing of a strong acid, and K plus is just that ion that is what? Soluble to all things. It's going to float around, so it spectates. So there'd be Br and K plus on both sides. They're not part of the reaction, so the overall reaction, okay, is going to be H plus plus OH minus equals water. Now, I show you this because most students want to write this every time. So this is really the exception. Very rarely do we actually do strong acid and weak base, strong base together, all right? And the reason behind that is because most chemicals that we do acid-base chemistry are either weak acids or weak base. There's more of them than the strongs, and we like to drive them forward stoichiometrically with the stronger counterpart. And I'll explain. So this is the overall reaction net ion. Notice the Br negative and the K plus are spectators like we suggested above here. The K plus and the Br negative. Okay, moving on. That is not normally what you're going to see, strong acid, strong base. But if you do, there it is. So here's an example of H2S. This is not a strong acid, okay? This is a weak acid. It barely dissociates. This is a strong base, completely dissociates. So when I rewrite this, I'm going to write H2S together. Because it's not a strong acid, it does not dissociate very well. It's a poor electrolyte, so it stays together. Calcium hydroxide, however, completely dissociates if it's in low concentration, and it's calcium plus 2, and there's 2 hydroxides. And I'll put the 2 hydroxides here just to remind myself that there's 2 of them. Okay, now what's going to happen is, well, this very, very strong base, okay, is going to rip the H away. So this is a strong base that's going to force the hand of the weak acid. Weak acids don't want to give up a proton, but they can be forced to stoichiometrically as long as there's enough of calcium hydroxide available, or in this case, hydroxide ions. So what we're going to make is, of course, a hydroxide, pulling off an H here, essentially, and we're going to make water. And I write water together because water is not a strong acid nor a strong base. And we also know it's terrible at dissociating. You'll say, how do I know? Its Kw is 1 times 10 to the negative 14. It is terrible at breaking apart into ions, so we keep it together. Okay? I hope you're keeping it together. Now, after H2S becomes, the conjugate base of H2S, after it donates a proton here, okay, it becomes H, S, and it's negative because it lost a proton. If you notice, calcium is going to do nothing. It'd be on this side as well. If you want to write it, you can. Okay, but we're going to get rid of it because the calcium is going to be a spectator. Notice the calcium hydroxide up here. Okay, it's a soluble ion. So we know it does make some precipitates, but that's not what this chemistry is about here. So I am going to get rid of the calcium here. So the calcium is on both sides, and we can get rid of it because it's going to spectate. Oops. And I'm going to get rid of this extraneous stuff here. And we can see, all right, that a hydroxide is going to pull an H off to make HS and H2O. All right. And there is your net ion reaction. I keep the what? Weak acid together. The strong base completely dissociated to calcium plus 2, but it's going to be some soluble ion, so I got rid of the spectator. There was no spectator of the conjugate base of the acid because this is not a strong acid. So this is going to stay together. And of course, you're going to make the water. And notice the entire charge here is -1, and the entire charge here is -2. You want to make sure that because we had calcium hydroxide with 2 hydroxides that were balanced here, but just carefully understand we have 1 H and then 2 H's on this side, right? So if we look very carefully here, we have 1 H here, we have 2 H's for 3, we have an H here, and 2 H's for 3. We have an O, okay, we have an O, and we have an S. So everything balanced, including the charge. This is -1 on this side. I'm sorry if I made that unclear. So that's our net ion reaction. Okay. So the charge is balanced and the mass is balanced. If you feel like you should be adding 2 hydroxides, well, then you'd be throwing a 2 in front here, okay, and a 2 in front everywhere. Okay, so it would reduce to the lowest whole numbers like this. Okay, so number 3. Let's be crazy and go to a new color because I feel like it. Okay, so HClO3. This acid listed above is a strong acid, okay? Very high Ka, so I'm going to break apart into H plus and ClO3 negative. NH3 is a weak base, so we got a strong acid, and we got ourselves a weak base. And again, if you just want to make sure. So there is my strong acid. There's its conjugate base, sort of, right? It's not really a base. There's going to be my spectator. Okay, so moving on down to where I was, and we can see that that's going to be a spectator. Okay, it's the conjugate base of a strong acid. So there it is in all of its glory. All right, so these guys will break apart. Ammonia is a weak base. Okay, it's not going to dissociate. All right, so it stays together there. And what's going to happen is this strong acid is going to force its proton onto the nitrogen part. You should know nitrogen loves to have lone pairs. And so we're going to make NH4 plus here. All right. And the ClO negative is just a spectator. I can write it on this side I want, but it's going to be on both sides. It's not going to do anything. Okay. So if I clean up my spectators, okay, you can see that this is my net ion reaction. The H plus from the strong acid, okay, protonated the weak base. And there it is. Simple as that. Notice this side is +1. And of course this side is +1. And all of the atoms and ions, or at least the atoms, are same number of nitrogens and hydrogens, so forth. Okay, so pretty straightforward there. Okay, and let's do the last one here. Okay, so we've got ourselves a strong base. This is going to break apart to lithium +1, hydroxide, OH minus, and this is going to break apart into Na plus, and I'll need some space here, HSO4 negative. Okay, looks really complicated, but some people get messed up or confused when they see like a K in front of something, or sodium or lithium. That's screaming, party people. That's a salt that's going to dissociate completely, because as I keep telling everybody, group 1 ions are soluble. Okay, so they dissociate. It's one of the reasons why they make strong bases or soluble compounds. All right, So it's kind of the same theme over and over again. So this is going to make the following ions. Now, we know that group 1 ions are completely soluble and spectate and do not have the ability to ionize water. So really, I know they're going to spectate. And I already know from the reasons we've explained, so I'm going to get rid of lithium and I'm going to get rid of sodium. Okay, I'm going to bring these back up. Plus what? Oh, HSO4 negative. Now, some people might say, I don't know what HSO4 negative is. There's an H in front, so it screams to you that it can donate an H. Or if you've got a table like my students have, you can see it's a weak acid. Okay? And that's a base. And by the way, strong base, weak acid. So notice the salt brought together, the negative ion of that salt was itself a weak acid. Now, weak acids don't like to dissociate, but guess who's going to force its hand? The strong base is going to rip the H away. You're going to make water here. Okay? And you're going to make SO4 negative what? Negative 2. All right? And that is the net ion reaction here because we got rid of the 2 spectators, which were what? Nothing more than group 1 ions. Hope you can see the pattern here. Okay? And so this is my overall net ion reaction. Now, some people like to, and I saw this today actually in after school, this is a strong base, weak acid. I know I had it written there. And so the strong base can force this to split apart by grabbing the H, if you want to think it this way. All right? This strong acid would force this guy to be protonated. All right? So another way to look at it. So there are our great examples, I think, I hope they are great, of our net ion equations where we got rid of spectators and only have those elements that are part of the acid and base reaction. Okay? Notice 2, 3, and 4, it's not H plus a hydroxide equals water. If we look carefully, okay, the only time you have that is with a strong acid, strong base. All right, so I hope that helped. All right, and again, really helpful to think about your strong acids and strong bases and who your spectators are. Your spectators are going to be the cations of your strong base and your, well, I say, quote, conjugate bases of your strong acids. Hope that helped. Good luck to you.